And next up, we'll have David Wang speaking. And he did quite a bit of isotope work already for his undergraduate and MSc studies. And he is now a PhD fellow at the University of Oxford, looking at development, assessment, and application of stable nickel isotopes as a novel geochemical proxy. And as Luke mentioned, both David and Luke participated in 2019 in the RGNO survey here of Namibia. So I believe David is going to give some results on the nickel isotopes he found here of Namibia. Without further ado, David, you have the word.
Thanks, Anya, for the introduction. And I'm David, and today I'm from University of Oxford. And today I'll be talking about nickel isotope in sediments, a case study in Namibian margin. And basically, I will extend from Luke's talk previously and have a special focus on nickel as one of the bioessential elements. And the following are my main collaborators in University of Oxford. And the keywords for my talk today are nickel isotopes, marine sediments, and trace metal. And I'll be talking about the importance of and potential of nickel isotope at the beginning, and then I will be sharing some preliminary results for this Namibia sample we collect 2 years ago. And I will have a brief summary and the work we're planning to do in the future. And as a bioessential element, nickel plays a key cofactor in many important enzymes, like hydrogenase. It catalyzes a reversible reaction between proton, a transformation between protons and hydrogen, and ureas. It catalyzes the hydrolysis of urea to ammonia and carbonic acid. And methyl coenzyme reductase, which we call it MCR, and all of the biologically generated methane derives from the catalytic activity of this MCR enzyme, and which it catalyzes the last step in methanogenesis. So overall, nickel plays an important role in controlling global carbon, nitrogen, and oxygen cycles. And due to the important characteristic of nickel in terms of methanogenesis, House et al. In 2009, they use it as an indicator in Van iron formation. They compiled several data sets for their nickel to iron ratio with different dated ages. And as you can see, there's around a 2-4 decrease around 2.5 billion ago for their nickel to iron ratio. And there's another 2-4 decrease in around 2 billion years ago. And it suggests that it's a reduced flux of nickel into the ocean at that time. And also suggests that it might caused by the cooling of upper mantle temperature and decreased eruption of nickel-rich ultramafic rock at that time. And in this example, it shows that nickel might be a good geochemical tracer to let us better understand the geological history. However, there's still some fundamental characteristic of nickel that haven't been well studied yet before we can use it as a robust geochemical tracer. So here is nickel in the modern ocean with a dissolved and particularly seawater profile. As you can see, the majority of nickel is in their dissolved phase, and there's some nickel removed from the surface ocean, removed from the ocean at the surface. and along with the depth, it regenerated, and nickel is released back to the seawater column. And there are several mechanisms that might cause the drop of nickel concentration at the surface, such as the biological uptake, the scavenge onto manganese oxide, iron oxide hydroxide, and it's also possible that some of the nickel is incorporated into sulfide in some sulfidic environment. However, if we want to address this mechanism, only based on nickel concentration might not be able to help us to do that. So that's why nickel isotope system come in. In nature, nickel has 5 stable isotopes, and we usually express nickel as delta nickel 60/58 compared with reference material. And 690-80s, a lot of effort has been put on the mass independent variation, isotope variation of nickel, focusing on cosmochemical studies to understand the planetary evolution or the composition of early solar system. In recent decade, people start to put the efforts on the mass-dependent fractionation due to its low temperature biogeochemical cycling and its bioessential characteristics of nickel. So if you see the nickel isotope for seawater versus the concentration, its concentration, actually we can see a positive correlation between these two factors. And some people suggest that the biological uptake at the surface ocean might be a plausible explanation for that. When the phytoplankton prefer to take the lighter nickel isotopes, so it goes to the right of the x-axis, and when it takes the lighter isotope, you leave the residual seawater to a isotopically heavy direction. So when the nickel concentration goes lower, the residual seawater goes heavier. However, if you focus on the data set here, like the red and the light blue one and the dark blue one here, there's no clear trend for this between these two factors. So some people suggest that this mechanism caused by biological uptake might be regional, or it might be a species-dependent mechanism. But as for now, there's no direct evidence that can prove this fractionation is really caused by the phytoplankton. So this is one of the questions we want to answer in the future. And there's another example for the nickel to TOC content in sediments from Peruvian alluvial region, which is another one of the most productive area, upbuilding area. As you can see, there's a positive correlation between nickel concentration and the TOC content, and with a slope for nickel to carbon ratio around 180 micromolar per molar. But if you take the average phytoplankton cells, if you take their nickel to carbon ratio into account, it's only about 6 to 12 micromolar per molar nickel to carbon ratio from the phytoplankton. So which means that in sediments, at least in organic rich sediments, only a few % of total nickel can be explained by an unmodified export from cells to sediments. So which suggests that there has to be another mechanism that enrich nickel into the sediments. So here, if we take the currently available nickel data in marine sediments, and if we start from left figure, if we plot it with aluminum to nickel ratio, which is the way that we try to separate the signal from the lithogenic source and oxygenic source. And one of the expansion that provided by the authors of this light blue dot from Guigan and Roxell 2021 that suggests the negative correlation between these two factors suggests is a mixing between its lithogenic source and oxygenic source. However, this trend cannot be seen in other marine sedimentary setting actually, and it's not seen in organic-rich sediments from a Peruvian upwelling system as well. Their isotope seems to be quite stable and quite close to seawater value with the increase of aluminum to nickel ratio. So we suggest that the controlling factor of nickel isotope might be different in different area. So it makes it is more complicated. And if you compare its isotope composition with manganese to nickel, the reason is that manganese oxide is considered a major sink for nickel in the ocean. And so there's a lot of work has been put to characterize the isotope fractionation during the formation of this or the formation or the associated process like absorption during this phase, like the manganese cycling, the dissolution, and the formation of manganese oxide, like the number the number one here. I note number one here. And it's also the isotope fractionation during the mineral transformation from bernstein to todorokite, which might also cause the isotope fractionation. And there's another isotope fractionation might caused by the scavenge onto iron oxide hydroxide or clays. And in this clause, it actually suggests that the mineralogy in these sediments might also play an important role in controlling the overall in the bulk nickel isotope composition in the marine sediments. And overall, and this current data set suggests that there's no simple or one expansion that can help us to expand all this data set. And I think the study using nickel isotope as a geochemical tracer in marine sediment is still at its early stage. So more data set are needed before we can come to a conclusion for what it really represented in the marine sediment. So there's some question that we need to solve before we can use it as a geochemical tracer. Like what is the controlling mechanism for nickel isotope in the water column, especially in the surface ocean? If it's really caused by the biological uptake, is this mechanism species dependent? Is this regional dependent? And what caused the enrichment of nickel in sediments? And what is the controlling factor of nickel isotope in sediments? And today I'll mainly focus on the question 3 and 4. So we're lucky that we can have the opportunity to be involved in the RGNO workshop 2 years ago. And yeah, there's some course, and we also have symposium, and we got a chance to go on research vessel Mirabilis to get a set of sample around Namibian margin. And basically, during the cruise, we went along 20 degrees south transect, 23 degrees transect to collect a set of samples, including sediments. And since Namibian region is one of the most productive area, so if we go away from the coast, we can get sediments in contact with anoxic bottom water, and if we away from the coast, we can get the sediment in contact with oxide bottom water, which gives us a really a good sample set for us to look into these problems. This is how basically how we collect the samples. We get the sediment cores from multicolor, and we use rhizome to extract pore water from it, and we also pump the seawater and get it through the filter to get particulate matters. So we get a sample set that we can do the further studies. So then I will be showing some preliminary results for our Namibia sample we collect in 2019. Let's start from the pore water part. The 2310 and 2360 means the data I'll be discussing today is collected from the 23° south transit, and the 10 and 60 means is collected 10 or 60 nautical miles away from the coast. And as you can see, in 2310, the pore water's chemistry suggests is more reduced environment than 2360, as its sulfate concentration start to be consumed as electron acceptor. And in 2360, you can see a decrease of iron and manganese along the pore water profile, which they're also being consumed as a electron acceptor. And if we see the sediment part, if we start from the left, we can see a significant difference of nickel isotope between these two cores. Is around 0.2 per mil difference for the average composition, with a slightly enrichment of heavier nickel at the top of the 2310 core. And for their nickel, manganese, and iron to aluminum ratio, there's no significant difference between these two core. And we got a higher TOC when the core is close to the coast, and got 3 to 4% of TOC in 2360 core. But overall, the TOC content in these sediments are extremely high compared with the average shell. And one of the question we want to ask is, does the TOC is the TOC content a controlling factor for the difference of nickel isotope in these two cores? So we plotted delta nickel 60 to TOC content, and we do see a weak positive correlation between 2310 between nickel isotope and TOC, but we didn't see it in 2360 core. And overall, it didn't show a clear correlation between these two, which suggests that the TOC content might not be a dominant controlling factor for nickel isotopes here. And as we mentioned before, if only a few % of nickel can be explained by the input from the phytoplankton cells, the fractionation during the biological uptake has to be super huge. It has to be maybe a few per mil. It has to be super huge, so it can start to make some difference in the bulk sediments composition. If we compare our data set with previous published value, you can see the nickel isotope in our sediments actually agree well with the other organ-rich sediments from Peruvian region, from Ciscado in 2018. And it shows a negative correlation between nickel isotope and aluminum nickel, which also suggests that it might be a mixing between lithogenic and ophthalmogenic end member with a steeper slope. when they're when we reach the intercept of axis, and this is possible that it might be explained by the different aluminum to nickel ratio in bedrocks in different region, which means that if in this region nickel is relatively enriched in the bedrock, it might be possible that our lithogenic source, when the nickel concentration is high, so that its aluminum to nickel ratio gets lower. So yeah. If we compare nickel isotope with manganese to nickel ratio, it shows a negative correlation between these two factors. It actually is in the trend actually is in the opposite direction for the process that some of the process that has been quantified in the lab, like the manganese cycling and scavenging of iron oxide hydroxide. But it still leaves room for this data set to be explained by the mineral transition from bernstein to todorite, because from the experiment, people suggest that during that mineral transformation, at least half of the nickel will be released back to the pore water, and it caused the negative correlation. However, in our preliminary XRD result done by my colleague Joyce, we didn't see a clear peak for bernstein. So it may be caused by the resolution issue or the detection limit issue, but as for now, we didn't see a significant influence from the manganese cycle or associated process. And the last thing I would like to share is when we try to calculate, when we try to correct the lithogenic contribution for our sediments, and when we use these two formula to correct the contribution from the detrital source, and we get a fixed a value for both city and earth, then we can use the mass balance formula to calculate estimate oxygenic delta nickel 60 signal in marine sediments. As you can see in the right figure, when the nickel to aluminum ratio is lower than 20 in these sediments, actually it shows some overcorrection issues, and the estimate oxygenic delta nickel 60 diverge, and the error become larger. But when the nickel to aluminum ratio is higher than 20, the estimate value seems to converge and get close to the deep ocean. So it might be possible for us to use it, but still have some slight isotope fluctuation due to this oxygenic phase. So we definitely need more constraint before we can use it as a geochemical tracer. And for this the gray dot here, the some manganese-rich sediments, and it suggests that the mineralogy might play an important role in this, as I mentioned before, since in their results, they show from their XRD result, they show that 2 to 3% bernstein has present in their sediments, and the nickel content in bernstein actually can be in a percent level, so it can make a lot of change in the bulk sediment composition. So here's my short summary that I think most of them I have mentioned in my previous slide. So based on our currently result, I think we're thinking to locate nickel in possible orthogenic minerals by using nickel exact analysis. If we know which minerals that nickel possibly locates, then we could try to quantify nickel isotope during the formation and associated process of this nickel carrier. Then we have a constraint, then we can use it as a robust geochemical tracer. And I think my talks will end here, and thank you.
Thank you, David. Yes, it was quite interesting. Is there anybody who has a question to David? Maybe clarity?
Yeah, if I may start, but my question would be, David, you do not see a correlation between the manganese oxide and the nickel that would be bound to those. Is that does that surprise you, especially in sediments of an anoxic shelf? Or in an anoxic sediment, you would not expect any MnO2 because that that would immediately be reduced, and then probably the manganese would be precipitated as manganese sulfide.
But yeah, that's true. But we do drop some figures with different trace metal and versus manganese versus TOC, but we actually they do see a good correlation between trace metals and manganese, and it's quite complicated. It's quite puzzling because those trace metals in these two core has a good correlation with manganese concentration and also with calcium concentration, also have a good correlation with aluminum concentration. So which is quite weird that it has a correlation with this different phase at the same time. So.
Isn't the nickel then scavenged as nickel sulfide immediately, especially in these sulfate reducing settings?
There's no direct evidence for any nickel isotope fractionation during the sulfide formation or the incorporation of nickel into sulfide. But it's possible that some people do see a microenvironment for cadmium. They do form cadmium sulfide during when they are settling as a particulate matter through the water column in the microenvironment. I haven't seen a direct evidence for nickel sulfide yet. Yeah.
Which surprises me. But there are other geochemists here attending, so they might comment on that. You know, it has always puzzled me that nickel and sulfide are combining to nickel sulfide, which is very insoluble. And especially in these marine sediments with a high content of sulfide. And the Namibian margin is a high sulfide sediment. So all the nickel should be scavenged as practically insoluble nickel sulfide. And still, you have lots of organisms that need access to it for their enzymes, particularly the methanogens that come a little bit further down. So that you exclude the possibility of nickel sulfide as a scavenger surprises me.
I didn't. I'm not sure how the nickel sulfide can plays a role in our sediment actually, because we didn't manage to measure sulfide content during our cruise because it has to be dealt with immediately after we collect the sediments. So that's one of the things that we couldn't manage to do during last cruise. But it would be interesting to look into it.
In the Black Sea, for example, the nickel concentration does not decrease with depth. So there's some scavenging along the redox line that's associated with manganese, but it's not associated with sulfide, and that's surprising, like you say, Kurt. But it's not it's not reactive with sulfide in this way.
And can you explain that? Why? Make a, make a simple precipitation calculation, and that nickel should all be precipitating as sulfide. What hinders that nickel sulfide combination and precipitation?
I can try to briefly comment. So if you look at I think if you look at the equilibrium thermodynamics, nickel sulfides are actually less stable than, for example, zinc or cadmium are also than pyrite. So you would rather form pyrite before you form nickel sulfides, probably. So it might get incorporated into pyrite, or if there's loads of sulfide, you might form some nickel sulfides, but it's not as stable as, for example, zinc or cadmium sulfides.
No, thank you, Tim.
Yeah.
Back to Dion.
Is there any other questions?
Well, I would have a question to Dion. You know, when you made your metal analysis, sediment with the Atomic Energy Agency, did you measure trace metals at all? And if so, what did you find?
Yeah, yes, we did measure trace elements in different matrices. It was one of them. We also did that in biota, and we've noticed from the biota point of view that it seems that nickel might be a concern for Namibia, also cadmium and zinc. We haven't analyzed all the data for the sediment has been analyzed, and we hope to bring a paper out before end of the year. I actually wanted to say to David that after you asked me a question, I went through the list, and I saw that we actually did around, I think, 15, between 10 and 15 sediment samples along the entire Namibian coast from Rudrits and up to the northern part, 18 lines. So the data is, we have the data available, as I said, but what's happening in the biota part, and the others were not trace elements. And also there's other 2 papers out on trace elements, and I can't totally remember now what the conclusion was, because we've done this papers last year. Yeah, but the papers are available. If you need to see them, I can send it to you.
Thanks, Dion.
Yeah, please do that. Something. What is todorokite?
Mm-hmm.
What's that?
Actually, I can't remember the formula for it, but it's another manganese mineral oxide mineral. It will transform from the bernstein like a layer phyllomanganate mineral to todorokite. And during this process, people suggest that at least 50% of nickel will be released because there's maybe less coordination place for nickel to incorporate. So nickel will be released from the mineral itself. So most of them will go back to the pore water. So makes the nickel concentration in the sediment lower. Mm-hmm.
Thank you, David. Yeah.
Yeah, I just
Tim-
have one quick comment, if I may, Dion.
Yes,
Just on the RGNO survey in 2019, I was just quickly going back to our cruise report, and for the 10 nautical mile station, David, we definitely found some sulfide in the water column. You know, the bottom water is just about 5 meters above the sediment. It was low, but it was just under 2 micromolar of H2S, definitely present. So, and this was on the 10 nautical mile station, on the 23 on the Walvis Bay transect. And the oxygen was also very low. It was about under 0.2 milliliters per liter there at the time of the survey. So just together with your sediment data, this is now obviously not sediment sulfide, but there would have definitely been some in the sulfides.
Thank you, Emil.
Okay, good. Is there any thing you would like to add before? It seems there's no more questions.
Yeah, I can just say thank you to both speakers, to Luke and David, for very interesting talks, and for Dion managing the panel. And I can also advertise for next week when Dion, I think next week it's Dion speaking, Dion and Krista Whittle, and we're going to be actually moving to phytoplankton, to more of the biological oceanography.